In this lesson, we will cover uh, argsort and how it can be used in an evolutionary algorithm to find the centroid of mu best offspring. And so I think the best way to sort of show that is graphically. So again, np.argsort is what we're using, and how it could be used in an evolutionary strategy. We will actually code an evolutionary strategy later on. So you might have to come back and check this out again later. Um, just so you can sort of refresh yourself in the future when we start doing that. Suppose we have some XY coordinates, and so the idea here is if you can see that you start off in the green, and then you randomly sort of throw out points around this little green point. So that's our parent in this generation. And then the way they're colored is we're trying to, it looks like we're minimizing in this particular case. And so this is probably the min. And you can see that these orange ones are the 4 best of 16 that was thrown out there. So I randomly threw out 16 based on that spot right there. So it's a sort of a normal distribution, and it reaches out. And you can also have a covariance matrix that can, you can sort of figure out what the new covariance matrix is as you move along in the optimization. But this is just one step, and so you start off with the green being the parent, 16 children get put out, and then we colored the 4 best out of that. And the idea is that now we want to find the centroid or the average or the mean of these 4 points, of these 4 orange points. And I just threw it in here to sort of give you a visual on what we're looking for. And this purple one would then be the new green, and then you would do the same thing. You throw out more points, find the 4 best. Hopefully they're down here. Hopefully you're not only getting ones that are above, right? So then you kind of be going backwards, and then you're sort of moving along the optimization. So that's the idea of it. Let's use a little simpler idea. Let's use mu is equal to 2, lambda is equal to 6, and you can see the numpy array, and then here's the values that go along with it. It's really, really small. I apologize. I guess I should have made that a little bit bigger. But this is the function. So all I did was I put in 1, 3 into the function and came up with 6, put 3, 1 into the function, and you get 0, and so on and so forth. And then I plotted it out here just so you guys can see it. The 2 green ones, if we're doing a minimization, I will say this isn't a great function to do it with. I think this one goes on to negative infinity. So it's not convex. It's not one that you would probably want to try to do a minimization. So if you were doing a minimization, you'd probably need some kind of constraint that would limit the direction or how negative you could get it. So negative 24, but that's not the point of this. The point of this is if I throw out 6 points, how can I then pull the fact that this is a negative 4 and this is a negative 90? These points have to be evaluated in order to get these, and then I'm going to use these points in order to figure out my 2 best. And so that's what we're going to use as argsort. Okay, with that being explained, or sort of hopefully you get a broad picture, let's go ahead and jump over to Spider. And these are the points. Let's go with restart the kernel. I had to get the picture up. So we'll restart the kernel and bring everything in. And we have our data here. So, the first thing I want to talk about, so that's why I put these little things in red so I don't forget to do it. Another fancy indexing facet that we didn't cover last time. And we're going to do this because this is not a really difficult lesson. Argsort, if we're just sort of talking about argsort and maybe how to get multivariable function, it's not that difficult. One of the fancy indexing facets that we didn't cover is, what if I just did 1, 1, 1, 1, 1, 1, 1? What would you expect it to do, and what actually happens? So 1, 1, 1, 1, right? So say that this is my index. This is the index that I'm going to pass in. And note that I didn't even make it a numpy array. You put this fn, and then what would happen if I did x, y of idx? You can see that there's one that corresponds. So that's 0. That's the 0th data point. This is the 1th one. So what happens is the 1, 1, 1, 1, however many ones you got there. So it doesn't really matter how big this thing is. Your fancy indexing will go in and it'll grab as many of these that you put in as it'll go in and grab it. Let's do another one. Let's just do a random one. np dot and int. Let's see, let's go from 0 to length of xy. And I don't know. So we're going to do 20 random. So note that we only have 1, 2, 3, 4, 5, 6 data points. And I got 20. So now I did 20 of them. So obviously there's going to be some multiple ones, right? So 8 1. So this is sort of the opposite of unique. So if I ran a unique on this and each one of these is in at least once, then we would have the same data set that we came up with. But this is sort of replicating. Maybe you're doing a bootstrap where you're doing some, what is it called? Random sample with replacement. So that's kind of the idea that you're doing here. So this is maybe a random sample with replacement, and I want 20 of them. So anyway, okay. So I just wanted to make sure you guys got that. And the next thing that we want to do is talk about a multivariable function. So I don't think we've covered this yet. I know we've covered lambda functions. So lambda x. So we're going to say that this x is a vector. And the way that we get vectors out is we do x0 times x1 squared minus x1 times x. And I should probably, I don't have to because of the evaluation rules, but I'll just put it in there just in case. And so that looks like the function that we want. And let's go ahead and say, oh, I want to evaluate each one of these. So I want to evaluate f of xy. Now you might think that when I evaluate xy, that it's going to go in and put 1 and 3 into here, and then it's going to go do 3, 1, and then 3, or negative 3, negative 5, and I should have 6 functional values that come out of here. But there's a problem. And the problem is that Python or NumPy expects this. So if you want this to work, it has to be, so I'll put it in here, pass in as column vectors. So right now, these are row vectors. So let me just print out xy again. So note that I just did xy, and I wanted to print that thing out. So this is row vectors. So if I want to turn that into column vectors, how can you do that? xy dot t. So if you do xy dot t, then so now when I pass it into the function, it's going to evaluate what 1 and 3 is, what 3 1. So that'll be x0, x1, x0, x1, x0, x1, and so on and so forth. So dot. So if you were to put 1, 3 in, you would get the number 6, then you get 0, and so on and so forth. Okay, hopefully that makes sense. I mean, don't try to put them in as row vectors. It doesn't like it. If you have a bunch of row vectors, then you can simply just do .t, and it'll pass it in correct. So let's do fval is equal to f of xy dot e, and hit F9. And as a matter of fact, I'm just going to print so we see what that sucker is again. And there it is. And now we're going to use argsort. So let's find out what argsort does simply by doing, let's call it idx is equal to np.argsort. And then I want to sort it by feval. So think about this. So I have these xy values, 1, 3, 3, 1, these numbers up here, but I want these to be mapped, right? So that's what a function does, right? It maps these values to function values. And that's what we want to do. I want to use this fval, this thing right here that we just printed off, to find the two smallest, so the one that's negative 90 and the one that's negative 24. So fval, and then print idx. And so look at what it gave you. So it gave you the index for the smallest, and I kind of wrote it right here what it's doing. So 2 would be the smallest. Does that make sense? 0, 1, 2, yes. And then 4 would be the second smallest. 0, 1, 2, 3, 4. 1 would be the third smallest. So 0, 1, so that's 0. And it looks like it's a tie with that one with 5. So 1 and 5 come up next, and then 0 would be 6, and then 3 would be 12, right? So that'd be our biggest. Now, how are we going to use this? Fancy indexing, right? Because this is now an index. So this is this 241503. I can just pass this in to my xy idx. That's why these sort of go together, these two lessons. I pass in 2, and I get -3, -5. So now we know, let's see, -3, -5, 0, 1, 2. So that's my smallest, and then 4 would be my next smallest. And then, and so on and so forth, right? So we just sort of reordered that thing. Let's go. So how can I get the best 2? Well, there's a couple different ways we can do that. You could say xy idx and then 0, 2. Right, so we could do that. We could say xy idx 0, 2. That's another way of doing it. I mean, there's a whole bunch of different ways to sort of index this thing in order to get the best 2. And then we could do dot mean, right? So if I'm trying to find the centroid of those 2, axis equals 0, then we'd get -2.5, -4. So this would be the parent of the next offspring if we were using this in an evolutionary strategy. Okay, and now the final thing is let's plot this bad boy. So PLT dot let me do this. IDX is equal to IDX 0, 2. So that's another way of doing it. And then we can go PLT dot scatter. Remember the scatter plot that we did last time? We're just going to do the same thing, except it's going to be XY instead of data. I think last time it was data. And XY of all the rows. And so this is going to plot all of these in the color equals blue. And PLT dot scatter. And then I'm going to get the other, just the 2. Move this thing out of the way. And the other 2, the best ones are IDX. So IDX is now, so these top 2 will be the numbers that come out of here. And then XY IDX. Right, and if you don't know what's kind of going on here, just run it. Just run these 2. So it gave you negative. So this would be the X values, and this would be the Y values, right? So that's kind of what's coming out of here, the 0th column, and then we're going to do color equals. I think I did green before. We can do red. Let's do red. All right, and then you're supposed to do PLT.show to let it know you're done, and then you get the same thing, except these are. I think these were green last time. Okay. That's really all I got. I wanted to show you. So come back and watch this video again once we start doing the evolutionary strategy stuff, and you'll see the importance of understanding argsort and being able to use argsort in order to get the best, however many. Again, we just use 2 here, but it could be 5, 10, whatever. Okay, that's all I got, and I'll see you guys next time.